Well, thank you very much for joining me in another session about my little TangerineTiger. Now, after the last session where we decided how the power was controlled, I've done nothing more on the machine, but I've done quite a lot of thinking. Can I start this session off with something rather shocking? I think I'm going to have to reserve the right to change the title of my little machine from TangerineTiger to Tangerine Tabby Cat. I don't think it's going to turn out quite the way that I or you were dreaming. That's a pretty bold statement, but let me just begin to explain how this machine actually damages material. And I think you'll begin to see some of my disappointment. Now, here in front of us we see the results of our mode burn. Now, this is the mode burn from my 70 watt constant current machine. This is the mode burn from the RF 30 watt machine, running in more or less constant current mode, 100% power. The same thing, but this time it's done with a beam expander, which is 3 times. This was 2 times beam expander, this is 3 times beam expander. Now, we talked about this last time, but we didn't really go into much of a discussion about it other than to say this was rubbish and this was more the sort of thing that I was looking for. Now, I'm going to have to explain myself a little bit about that and why I want this rather than this. Ideally, I'd like this. But hey, several things about this RF laser are different. First of all, coming out the laser, the beam is not parallel. It expands quite a bit more, maybe 2 or 3 times more than that coming out of a glass tube machine. That was disappointment number 1. And that, in fact, means that we put a beam expander in there like that to make the beam parallel. Okay, now that automatically cost us, as we found out last time, 2 lenses in here cost us roughly 4% and 4% power. So we've already lost power because we've had to adjust the beam. I've had quite a few people ask the question, why didn't I use a 3 or 4 times beam expander? Because I've got plenty of room on the mirrors to do so. It's a difficult question to answer to somebody that cannot see what I can see. They're believers in what I call conventional lens theory. And here we have a lens facing the work, which is down here. Coming onto this lens, we have parallel beams of light. Now that beam there happens to pass right through the axis of the lens. This lens is designed to focus the beams, i.e. it's trying to collect all the power into one spot. So the beams that are on the outside here come in here and they focus, say here, like this. Now, these beams that are slightly closer towards the axis take a slightly different path, and depending on the type of lens, whether it's a plano convex or meniscus, if it's a plano convex, then they won't take the correct path and they will actually focus a little bit further forward, like that. Okay, and the closer we get to centre, the further forward the focus point will move. So let's just take the extreme situation of this beam here that passes right through the axis of the lens. Where does that focus? It's a single beam and there is no other central focus, only one. The answer is really not 8 meters away or 8 millimeters, that's infinity. It will never cross over itself because it is itself. We've only got to move marginally away from the centre and they will converge. But where will they converge? Well, the answer is probably a long way. If we look at these rays and say, well, that ray is going out there, that ray is going out there, this ray is going out here, and this ray is coming out here, what we're finding is what you consider to be the focal point is this. Look, we've got the line here which does that. And that is what you would probably consider the spot size or the focal point. So there is a footprint at the focal point through which all the rays will pass. Now that's the important thing, all the rays will pass. It doesn't mean to say they all focus at that point, as you can see. Some of these rays are focusing way beyond the focal point. Now if this source of light here was uniform, there would only be a small proportion of that energy which is focusing below the focal point, and you would probably hardly notice it. But that's not the case with a laser beam, because our laser beam has got an energy distribution which looks like that. In other words, we have got something like about 70% of the energy in roughly 1/3 of the width of the beam. That means that we've got an extraordinary amount of energy concentrated around about the central axis of the lens. Now, I've demonstrated this in several of my videos, that there is a lot of power below the focal point that we can work with. The reason why I'm telling you this is because the discussion about maybe using a beam expander to get a better focus, I agree, probably you would get a better focus. So we're going to take this Gaussian distribution when it is coming out of the laser, but by the time we've expanded it out to some other dimension, what's happened is our distribution is no longer like this, it's more like this. In other words, what we've done, we've taken away the potential for this high energy which passes through the centre, and we've pulled it out away from the axis so that we can tame it and focus it. And so we should be able to focus that beam a lot better if it's bigger. Is that what I want? I personally do not want that. I want my beam to be untamed, and I want this central core of energy, because that is what I believe is going to do the damage to the material. I'm not interested in this thing called a spot size or the focal point. I want something else. Okay, so that is why I have opted for exactly the opposite of this. I'm trying to keep my beam as sharp as possible. There we go. We can prove that point there, look. Opening the beam up makes it a lot blunter, and if it's blunter like this, then we're going to be able to focus it better. That is how standard lens theory works, and I agree with that completely. It will focus it better, but that isn't what I want. Let's go back to the pictures that we had last time, where we saw we had control of the laser power with a square PWM signal. What we have here is 30 watts. Every pulse is 30 watts. We have no other wattage in this unit. It always delivers 30 watts. So how do you control the power? Here is one cycle. Now in that one cycle we have got 50% high and 50% low. Now when I say high and low, I mean that is 30 watts of power, and this is 0 watts of power. The actual RF laser is switching on and off and on and off all the time at varying frequencies, which we talked about. We can modulate the frequency, but don't worry about frequency because that's not the issue. The issue here is that we control power by changing this ratio here. Here we are, percent power. 50% power means we've got 50% on and 50% off. 10% power means we've got 10% on and 90% off per cycle. Okay, so 50% on and 50% off means that on average That bit there fills in this bit here. What we've got is a total of, instead of 50% power, we've got 50% of 30 watts. So actually, when we operate in this mode, we've actually got 15 watts. Because it's only on for half of the time. Okay, now let's just take a look at compare this to our constant power laser beam. Here we've got a surface. Here I've got my constant power laser beam moving along at a constant speed. So if I switch the laser beam on, it will dig itself a hole. Because it's constant power, the hole will be like that, and then it will switch off. So it'll make a hole like that. Now, if I made that hole at, say, 200 millimeters a second, and then I change the power on the laser beam to 100 millimeters a second, what do you think would happen? So I would probably expect to make a groove twice as deep, because I've got the machine running so slowly that it's able to do more damage before it moves on. So this is 100 millimeters a second of damage, and this is 200 millimeters a second of damage. So the depth of cut is proportional to the speed. I'm going to put for CW, which is constant wave, which is when this machine operates at 100%, or when we use a constant power laser. This CW and our standard laser that we're used to, our glass tube, which is on permanently and not pulsing, would produce these shapes if we ran across at these speeds. Let's assume that we said in both instances this is 100% 30 watts, and this is also produced by 30 watts with our glass tube. They would both produce exactly the same result. Now, I gave you some false information when I spoke last time. I said to you, imagine a candle flame and holding your hand over a candle flame. Now, a candle flame has got a constant output power. And I talked about sharing power. By moving your hand across slowly, you share the power out a lot less, and it settles in one spot more, and you will burn your hand. But if you move faster, you can share that power out to such an extent that it doesn't damage your hand. I said, but that wasn't the case with this pulsing system, because when you share it out, you get a nice gentle beam like that, and when you have a pulsing system, every pulse will be the same power. That was a bit of a misleading statement, because now that I sit down and look at how this thing works, it doesn't work like that at all. So for convenience again, we've got 50% on and 50% off. Let's just see what happens. We know that this will always be 30 watts of power. It cannot change because the signal is controlled by this 5 volt value here, and we're not changing the value of this 5 volts at the moment. Okay, this is the way in which it operates. We change the power by changing the duty cycle on this square wave. If we've got 30 watts here and it reaches this point here, switches on and produces some damage in the surface, switches off, switches back on again, switches off. So we're going to damage the surface like that. If we have our constant laser running at 30 watts, we produce a groove like that. Not perforations, but a continuous groove. If this was running at 200 millimeters a second, and this was running at 200 millimeters a second, this little bit here and this little bit here. Is there any difference? I've got 30 watts cutting that deep, and here I've got 30 watts from my glass tube cutting that deep. There can't be any difference because they're both 30 watts, so they both do the same amount of damage. Now, come back to my burning hand principle. The faster I run, the more I will spread the power out. And so consequently, if I change this from 200 to 400, my depth of cut is only going to be that deep. Because I'm running twice as fast, therefore I'm spreading the same amount of 30 watts over the surface. And I'm doing half as much damage because I'm running twice as fast. Does anything miraculously change with this system? If I run this at 400 millimeters a second, so I was totally wrong when I said that to you. I'm not going to get little power pulses across my hand. I'm going to get the same perforation pulses across there, like that, at the same energy density as I would if it was continuous. You have to imagine that in this instance the candle flame is going on, off, on, off, on, off at a rapid speed. So all I will get is a perforated line instead of a continuous line with the same amount of damage or the same amount of hurt on my hand. I'm puzzled at the moment as to whether this is going to do more damage. It looks on the surface there as though I'm going to do half as much damage with this laser as I could do with 30 watts continuous. I'm trying to work out what the advantage is of having a pulsing laser. And of course this is assuming at the moment that the pit that we make is a dead copy of the on-off. It could well be that this pit is something like that because the power doesn't get a chance to build up quickly. It's not a straightforward cut. For instance, if we had this at 10%, like this, what sort of shape pit would I make? At 200, would it be that depth? Or would it not get a chance to build up even, and maybe I only got a little shallow cut? These are all facts that we're going to have to try and find out. So undoubtedly this system can react a lot quicker than a glass tube system, but it depends how you use the glass tube system. You can emulate this process with a glass tube. We're going to have to do some tests to find out about this. How good is the relationship between this square wave here and the damage that we do? I'm going to have to use this to start with because it's the best way that I can see what's going on inside there. I can modulate this frequency along here. If I change that to something like about 500 hertz, which I can do, I'm allowed to do that because it says I can run anything between 0 and 225,000. I decide to set the speed of my cutting to 1,000 millimeters per second. How long does it take to travel a millimeter? So there's 1 millimeter, and there are 1,000 of them in a second. So that means that 1 millimeter actually equals 1/1000th of a second, which is 1 millisecond. So every millisecond I travel a millimeter. How long does it take for a single cycle? If there's 500 of those in a second, it's 1 divided by 500, 0.002 seconds. 1 second divided by 500 increments, 2 seconds, 0.002, which equals 2 milliseconds. So we're going to travel one plus cycle and one minus cycle. I should be able to run at 1000 millimeters a second and 500 hertz and produce a shape on the surface which looks like that, where that's 1 millimeter, that's 1 millimeter, and that's 1 millimeter. That should be very, 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 very visible, and that will tell me exactly what's going on. So in the previous diagram we showed that you could reduce the depth of cut on the RF and the constant power laser by changing the speed. Spreading the power out over more time, over more distance, whatever it is, you can spread the power out and reduce the effect of 30 watts, whether it be from an RF or a glass tube. So even though I've still got the low speed, 200 millimeters a second, if I reduce the power from 30 watts to 15 watts with a glass tube, I can make the cut half as deep. So I have two ways of adjusting the cut depth on a glass tube laser. Do I have the same options on the RF laser? Well, the answer is no. Look, I've got 30 watts here, and I've always got 30 watts. Even if I make this into 10% and 90%, all I should finish up with doing is producing a hole like that. It will be the same depth because I've got the same amount of power, 30 watts. So I cannot change the depth of the cut with power. You can say, well, yeah, but look, you have just reduced the power. I've reduced the average power. I haven't reduced the specific power in a pulse. The average over time has reduced, but not the power per pulse. So the only way that I've got to adjust the depth of cut with an RF laser is speed. If I increase the speed, I should decrease the depth of cut. Now that's a very important fact and a big difference between the two systems. Now I've got no idea why the big boys decided to choose an RF laser, other than the fact that it's not Chinese. They may or may not have realised the mechanics of engraving. When I watch their videos, I have to say they do not understand the process that they're selling. That sounds a bit arrogant, and I'm going to explain why, and you can go and look at some videos, some demonstration videos, and you'll see exactly what I mean. You need to understand the basic principles behind engraving. It's not even engraving, it's material damage. So here we've got a surface, and I'm going to fire a laser beam at this surface. Now bear in mind it's a laser beam which is focused down to a point, and that means that I'm going to put an incredible amount of power into the surface of this material. Now we won't talk about the material for a minute, we'll just call it a material. The first thing that's going to happen is we're going to produce a little bit of damage there, and that little bit of damage is going to convert solid material into gas or vapour. If I gave you a cup of water and you boiled it and didn't have any windows open in the room that you boiled it in, that cup of water would fill the room with steam. You know intuitively that vapour takes up a lot more room than solid. Obvious fact, but one that everybody seems to ignore when they're working with these machines. If you convert a small amount of material into a vapour, it will do exactly what this is shaped like, and it will produce vapour which explodes upwards like this. If you try and tunnel down deeper, you're converting material, much more material, into vapour. But hang on, this vapour here is in the way of the vapour that wants to expand up there as well. And so it doesn't. What it does, it expands out sideways like this, because it can't go upwards because there's so much vapour going up that's in the way. And so consequently you get a lot of sideways spread. The more material you try and convert, the more you're going to get this sideways spread, a sideways explosion of expanding gas, because it can't physically move up quick enough. And that is the stuff which, if you happen to have stuff that's blowing down onto the surface, which I hasten to add, when you look at the big boy machines, they always have air assist on their engraving. They say it blows away the fumes. No, it doesn't. It blows the fumes back down onto the work, where they condense and produce the horrible brown surface that you see on their work. They do not understand this very simple mechanical principle. It's not even chemistry. The basic principle in engraving is very simple, and I learned this a long time ago. If I'm trying to engrave a letter like that, which is solid, click, 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 like this, that's the last thing I want to do. I am going to scan across there, but what I really want to do, I don't have the option on a glass tube machine of being able to go blip, 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 like that. Now, the way that I achieve that on a glass tube machine is to take that letter there, but I will convert it into a bitmap. I will make the black into grayscale, and I will make the grayscale into mid-grey. Why? Well, because mid-grey, when it's converted into a dithered image, and I know this sounds a long way round, but when you convert it into a dithered image, I get this: 50% black and 50% white. I get dots like this. Hang on. Isn't that what we've got here? The ability to produce dots? Of course it is. The RF laser does something in a simple way that I have to approach in a very complicated way on the glass tube machine. Now, why am I doing this? You might say, well, hang on, you're going to produce a grey letter. No, I'm not. I'm going to produce a black letter because the dots are always one colour. It's just that it's not going to be a continuous line. It's going to be a series of dots like this, which to the naked eye will look like a solid line. The advantage is that all I'm going to do with these dots is to produce little teeny weeny explosions like this, and my fumes will go upwards. Now, if I've got my air management through the machine sorted out properly, those upward fumes will not be blown down because I'm not going to use air assist on engraving. They're carried away by the high velocity airflow that I have over my work, and they do not get a chance to settle down. This is particularly useful when it comes to engraving some really dodgy materials like leather. Leather produces huge amounts of fumes. The oils and the organic products in the surface, it just absolutely cakes the place with brown if you do continuous scan lines. The only way you can engrave leather in any way, shape or form is to convert it to a bitmap and dither it. But you dither it to 50% white and 50% black, mid-grey. Then you can produce a nice clean image on leather or wood or any other material that you choose to use which produces nasty fumes. And acrylic is one of them. The fact that this RF tube can produce small controllable dots at high frequency has got great potential as far as I'm concerned for engraving. It might be crap as a cutting machine, but it has potential as an engraving machine if it's understood how it works and you utilise it properly. Now, I've not seen any evidence of proper utilisation when I look at some of the demonstration videos on YouTube. They talk about resins and saps being pushed up and flowing, and how you clean them up afterwards with just a damp sponge. No, you don't clean them up with a damp sponge. You don't even let them settle. we have found a big positive, maybe, for an RF laser. The first one. Now here's our standard PWM, 25 kilohertz, and we've got it set at the moment to 50% power. 50% on, 50% off. So we've actually got 15 watts going into our job. But as I said, we haven't got 15 watts. We've actually got 30 watts going into every pulse. But the pulse length is 20 microseconds long. That's not very long, 20 microseconds. So a question we ask is, how much damage can we do with 20 microseconds of 30 watts of power? Now that's a difficult question to answer. If it's a piece of wood, maybe it can do that much damage. If it's a piece of leather, it may be able to do similar sort of damage. If it's a piece of acrylic, the chances are it may be able to do that much damage. If it's a piece of glass, it may be able to do that much damage. MDF is very similar to acrylic. I know this because of all my experimentation. The materials themselves do not respond in exactly the same way. I mean, for instance, acrylic has got a melting point of 160 degrees C. That's pretty low. And it boils at 200 degrees C. So you say, well, they're very, very low temperatures. I mean, wood, for example, you have to be maybe 200 degrees C to make it scorch, and probably about 350 degrees C to effectively start burning it. And then you have to be about 4,500 degrees C to burn away the carbon. Look, 4,500 degrees C, wood is easier to damage than acrylic, which has got a threshold of disappearance of only 200 degrees C. It's all to do with the atomic structure of the material and how this 10.6 micron wavelength is able to excite the molecules in the material. These molecules here are easily excitable, whereas these molecules here are much more difficult to excite. So it requires more power to cut acrylic and MDF than it does to cut wood or leather. 20 microseconds on wood might work and produce that amount of damage. How do we get the same amount of damage onto acrylic? Well, the answer is we've got to allow more damage time. That might have to extend out to, say, something like about 60 microseconds. Now, if it requires 60 microseconds of energy, 30 watts, to do that amount of damage, that means the only way that we can get 60 microseconds is to change the frequency. We've got to reduce the frequency from, say, 25 kilohertz to, and bear in mind we're now going to go from 20, which is the damage cycle, to 60. So we've got to go 3 times as long, or roughly 1/3 of that frequency. So we've got to come down to about 8 kilohertz. And at 8 kilohertz, we shall have 60 microseconds on and 60 microseconds off, if we happen to be using 50% power. We could achieve 60 microseconds by choosing a different frequency and a different relationship. In other words, not 50%. We could use a slightly higher frequency, 12 maybe, and use maybe 60% on and 40% off. We've got all sorts of combinations that we can use, but that's why we've got control of the frequency and the mark space ratio, or the duty cycle. That's why you need to understand the difference between duty cycle and modulation, because at the end of the day it's the pulse length, the amount of time that you allow the beam on, that's going to cause the correct amount of damage for the material that you're using. It's got nothing to do with this average power. It's all to do with the pulse power in one single pulse. And because it's so important, I'll try and sum it up very quickly in a few words. Average power has got nothing to do with pulse power. You control this machine with pulse length, and pulse length comes from a mixture of duty cycle and modulation, the frequency. So that's enough theorising. Well, a lot of it's not theory, it's fact. The only thing that we don't know is the relationship between this fact of the electronics and what happens in the real world. What is the physics response to that electronic signal? How quickly can the light generate enough photons to damage the material in relation to this signal? I think the answer is we probably won't notice the difference. The only thing that we shall notice is actually this problem here, the difference between the materials. And we're not using the best material in the world, acrylic to start with, but it's the only material that we've got that enables us to look through the edge and see what's happening. So let's go to the machine and see whether we can make this happen. Okay, now look, I've drawn a line here which is 20 millimeters long, and here are the parameters that I'm going to set for it. We're going to set it at 1000 millimeters a second, 50% power. Now remember, 50% power isn't 50% power, it's 50% average power, where I've got 50% high, 30 watts, and 50% low, 0 watts. Okay, so I've still got 30 watts here for 50% of the time. That's the important thing to remember when you see these numbers. I can go in here to advanced settings now. So I'm going to set the modulation now by ticking this, and I'm going to choose, instead of 500 hertz, which gives me 1 millimeter pulses, I've chosen 250 so that it gives me 2 millimeter pulses. This line is not very long, and I've asked for 1000 millimeters a second. Now, I haven't messed around with the accelerations on this machine at the moment, so it's going to accelerate quite slowly. And it's not like scanning this, it won't accelerate and then produce a line and then decelerate. This is not scan, this is cut. So what we shall see on this here is likely to be a start off from 0, which means we should have quite a deep cut because the speed is 0. And remember, even though we've got long pulses, we shall also have slow speed, which means we shall get a deep cut to start with, and as this speeds up and gets towards the middle of the line, and hopefully by the middle of the line it will have reached 1000 millimeters a second, and then it will slow down again. So we should see deep cuts, maybe some nice 2 millimeter pulses in the middle, and then we should see some deep cuts again at the end of the line. There we go, it was as interesting as that. So this image is basically the line tipped up at 45 degrees so that I can see what's happening. You've got a reflection internally within the perspex of the image. So the one at the top is the reflection. The one that we're looking at is the bottom image. And there you see we've got our acceleration from 0, where we've got a lot of cut depth. Gradually the cut depth gets shorter as we accelerate, and then we move up to some sort of speed which is not 1000 millimeters a second, and look, we've got some pulses, but those pulses are only 3/4 of a millimeter apart, so they're not running at the correct speed. And then we slow down again, and you can see the depth getting deeper, and we get to the end of the cut. So that was pretty unsuccessful really, wasn't it? Apart from proving the point that the cut depth is dependent upon velocity. Now, to ensure I get 1000 millimeters a second, I've done two things. First of all, I've been into my vendor settings and raised the limit from 500 to 1000 millimeters a second, so that when I get to this layer here, I can actually use 1000 millimeters a second. Now, I thought I was doing that when I did the single line, but I think I might have made a mistake. Always admit to my mistakes, because hey, that stops you making the same ones maybe. So there's nothing wrong with this now. Scan, because I'm going to use scanning, and I'm going to put lines that are 1 millimeter apart. So I've got about 4 or 5 lines in there, 1 millimeter apart. That should give us an idea of whether or not we've got good separation and good response time. When I did the line test, look what I've put in there, 250. That's not 250 hertz, look what it says here, 250
kilohertz. There we go. So my two grey cells let me down again. They didn't quite spot the fact that it said kilohertz. So if we want 250, in fact we'll go to 500, which is what we originally thought we'd do, which will be 0.5 kilohertz. 500. Okay. Just check that it's accepted 0.5. Yeah, it's happy to accept 0.5. So we should have 1mm space, 1mm line, if we've got all our calculations right. And if the material responds at a fast enough rate. It's not going to be very exciting, but hey, let's go for it. Look what we've got! I think we have to be pretty impressed with that, haven't we? Because not only have we got 1000mm a second out of the machine, so it tests the machine accuracy, because we've got exactly 1mm gap and 1mm spacing across there. It also tells us that we've got an incredibly fast response time switching the pulses on and off, and that our acrylic is not as dead as I thought it was going to be. If we try and go deeper, we might not have completely square corners, but I'm pretty impressed so far. The only way that I can make that pulse deeper is to compromise on the speed. So if I run at half the speed, I should get twice the depth but still get 1mm spacing. We'll now run this at 500mm a second. It's under the microscope to see what's happening, but I can assure you that it's very, very interesting. Now these are the pulses at 1000mm a second. And you can see that I'm looking through the edge of the material and tipping it up. Okay, so we've got, you can see the depth of the pulse there, and it's looking pretty good. So there's the depth, but when I tip it up, you get a reflection. But even so, they're looking pretty crisp. Now, when we halve the speed, here's what we got. They're quite sharp-edged pits. They're not quite as rounded as I expected them to be. They're sharper than I expected them to be. But they do look shorter. Now, why would that be? What did I not think about? So, if I halve the speed from 1000 to 500mm a second, my 1mm per millisecond is going to change down here to 0.5 millimeters per millisecond. So therefore I'm only going to see a 1mm because I'm going to have half up, half a millimetre up and half a millimetre down. So if I keep the frequency the same, I've got to halve the distance, which is what this is telling me. But in addition to halving the distance, what it's also done is doubled the depth, because we've kept the pulse on longer. So if I want to go back to 2mm spacing, I've actually got to change the frequency to 250 Hertz, not 500 Hertz. I hope this little demonstration of my mistake shows you how heavily related that speed, frequency, mark-space ratio are intertwined together. I ran exactly the same tests on a piece of poplar plywood. All the same settings. Then on a piece of MDF, and then on a piece of glass. All very interesting and actually quite a lot better than I thought they were ever going to be. Having started off asking the question, am I going to be disappointed? I think we're coming up with a slightly better answer. There is no magic, there's a lot of complexity, but I'm quite actually excited again for the future. So on that happy note, I'll thank you for your time, because my head hurts, I don't know about yours, and I'll catch up with you in the next session. Bye for now.